1, 2, 3. Glad you could join us. All right, just an announcement for everyone. If you do get a nasty email from the attendants, people saying that you didn't swipe today, that's okay, ignore it. After class, hopefully I will remember to turn off attendance taking. Now that we're done with, I literally just said 15 seconds ago that there's no need to swipe, but that's okay. Don't, short attention span, I get it. So no need to take attendance anymore. We're done with that, so let's get into it. Test is on Monday. Thank you, 4th of July, for the wonderful 3-day work week. Couple of things to note. Problem set 3 is now out. One thing to notice is that I've skipped problem 11. No need for that. The other thing is that on problem set 2, there will only be these 6 problems. These 6 problems are due on Thursday. The other 4, 7 through 10, these are due on Friday at 6 p.m. They are now part of problem set 3. So the problem set 3 on Friday is kind of a big deal. The thing about these, now a couple of pieces of advice for this homework. Problem sets 1, 2, and 3 are directly from spring 17 to 14. So look for all of the tutorials on YouTube, and they should pretty much take you everywhere you need to go. So you can do that. Also, today, tomorrow, and on Friday, those are homework due days. The TAs will be in the tutoring room, which is now in 109, for the next couple of weeks. So you can go in there and talk to the TAs. So that's it. Let's go do it. Oh, 214 test 1 samples are on Blackboard for last summer and this spring. So you can, or maybe even the spring before. So you can take a look at those and see how they look like. I mean, it's the same format. In class on Friday, we learned about the beginnings of circuits and how if you've got a basic circuit, it will kind of look like that. You've got a resistor, which provides resistance. You've got a battery, and I think we're going to use this new word called electromotive force. And this is the ground. And one of the things that we need to be very well aware of is, thank your lucky stars that you're not an electrical engineer, because I'm going to tell you one of the things that I taught Physics 212, the Cal-based physics, twice. There were electrical engineers in the class, and I've decided that if I ever taught that class again, if you're not aware of the units of resistance, of electromotive force or potential, or what we would call, or some would say, potential difference, And if you're not aware of current and how it is used in amps, and that an amp is a coulomb per second, if you're not aware of those basic units, we've got problems, especially if you're an electrical engineer. I'm insanely passionate about the units. I think they're very helpful to keep track of. If you're an electrical engineer in this class, you're taking the wrong course. But if you were an electrical engineer and you don't know these basic units, I would have written a letter to the electrical engineering department letting them know that you couldn't even understand the basic units. These are some of the things that you're just going to have to know. The battery provides the force, the push, sort of like a strength of a fan, pushing air. The air itself is the current passing through like pipes. You can even think of like a pump and water. The water is the charge, the rate at which it flows through the pipe is the current. The resistor is kind of like, I think of it kind of like waterfalls. As the water goes down, it releases energy, it gets work done. And so these are kind of the basic understandings. If I think of this as kind of like like you've got the water wheel, and it lifts up water, and then it goes down a waterfall. This battery would be the water wheel. The waterfall is kind of like the resistor. The base of all of this is kind of like the ground. And so this is how I tend to think of it. The big equation that we use for all of this is Ohm's law. And that current is voltage over resistance. That if you took the battery and you divided it by the resistance of the circuit, you would get the current flowing through it. And Ohm's law works on large scale, complex, and small scale simple circuits. Now, this would be a very simple circuit. You've got the potential, you've got a resistor, you've got the ground. Let's draw this again with some more interesting numbers, or some numbers to begin with. Also for electromotive force, the symbol that you occasionally see is that. That is occasionally mentioned as electromotive force. That is a Greek lowercase e, I think, and or lowercase epsilon, or no. Oh, I can't remember. I'll get back to you on this, but this is what it looks like. It looks like a weird script E at the very least. And so let's say we had a potential of 20 volts and a resistor of 200 ohms, and I want to know, oh, and I'm going to put the ground here. In 214, the traditional location of ground will be directly behind the battery, just sitting at the base. Now, we went over on the lecture on Friday over the different ways, like here, the ground means that along this red line, the potential is all the same. The potential there is 0. Any region that does not pass through or a resistor or a battery has the same potential. And you could even say if it doesn't pass through a capacitor. So the potential all the way over here, all this wire doesn't pass through a battery or a resistor, so it all has to have the same potential, and which is 0. Why is it 0? Because it's connected to the ground. The ground is, you treat the ground as an origin. Treat the ground as your reference point. And like any good origin or reference point, there is only one. So there cannot be, well, I guess in more complex electrical engineering classes, you can have multiple grounds. But in terms of Physics 214, there will only be one. There will only be one reference point. When you go across a battery, you go here and you go over there, your change in V is negative V. So if you go from the positive to the negative end, you go from the high potential to the low potential of the battery, you decrease altitude, so the change in potential is negative, whatever that battery is. If you went from there to there, there is a positive increase in potential. That battery potential, or the battery potential, lifts up your potential to there. Which means that the potential at this point and along this wire, the potential at all of those points are 20 volts. So really what we've done is we've labeled all the altitudes of the of this circuit. This is very similar to saying, to do an analogy with just the altitude. And even though it isn't that dramatic of a difference, you can think of the floor right here next to me as the base of the circuit, like the ground. And you notice that the slope of the room goes slightly up. So let's just assume that the battery is along that side, and so it lifts, the electrons are moving around and the battery lifts them up to a higher potential. And then the resistor is kind of like at the far end of the room. The slope of the room comes back down. So the water goes up, it goes along the back, it comes down. So this would be the top of class, or top of the room, or actually, if we're using more literal terms, the back of the room. And then all of this is the front of room. And one thing that we do need to know or note, that if I were to start here, traveling all around the loop, my delta V for the loop is equal to 0. That if I start at this floor and I walk to the back of the room and I walk along the back and then I walk back forward and I stand right here, what's the change in height from beginning to end? Nothing. Just as I took my hand at the beginning for all that potential energy when I was talking about gravitational MGH, and I said you start here and then you do all of this weird stuff and then you end up right back there. As long as the starting and the end points are the same in terms of height, the change in potential energy is 0. As long as your starting and end point for a circuit is the same, the change in potential is 0. So it's something that we're going to use in physics for the next month. Now on this simple circuit, you only have one resistor and you only have one battery, and this is a great thing because it makes things simple. If I say, well, what's the current? You would use Ohm's law, V over R, so that's just 20 over 200, and that gives you 0.1 amps. So that's the current of the battery. If you were to measure the current going through the circuit, you would get 100 milliamps. Circuits, oh, and then the other thing about this lab, you're going to be using Ohm's law in a particular way, exactly like this. If you take I equals V over R, you will be using it, using this equation in several different ways. You can in one particular way, you're going to change the voltage and then you're going to read the current. The current is the dependent variable. The voltage is the independent variable. And if you compare it with y equals mx, y is a function of x, y versus x, the similarities are that I is your y, V is your x, and your 1 over R is your slope. So what's going to happen is today you're going to have a list of potentials, a list of currents. You're going to plot this thing out, fit the line, and then what you're going to do is you're going to find out that slope, and the resistance of that circuit is 1 over M. So if you take the inverse of the slope. Now this is for the very simple circuits, like one resistor, and we're going to talk about the variance coming up. When you have a circuit, and let's do something, well, what we're going to do is we're going to do a little bit more of a complex circuit. And say you've got something like this. And let's say this resistance R1 was 50 ohms. This resistor was 25 ohms. R2, and then R3 is 10 ohms, and the battery is 10 volts. And I ask you a couple of questions. And so with this simple problem, we're gonna talk about it for 20 minutes or so, because it introduces a lot of problems. One is, I'll write the symbol down. What is R sub EQ? And this symbol is equivalent resistance. I want to know I naught, and that is the current through that battery. And then the last thing that I want to know, well, actually, we're going to break this down in all sorts of parts. I want to know the potential at all 3 points. What is the potential at those? And it's going to be, we'll get to this. Also, I want to know I1, I2, and I3, the currents going through each of the resistors. So I want to know that, and that, as well as that. So you have the battery, you have the 3 resistors, you've got a current passing through the battery, a current going through those 3 resistors, and then you want to know the potential at those 3 spots. Now, before we even get into any of this equivalent resistance nonsense, the thing that we can attack first as being the trivial parts of the problem are, and as always, there is a ground behind the battery. The first things that we can do is knock out VA and VC. Those are the trivial parts of the problem. How do we know that? Well, we know that every part of the wire adjacent to this ground that doesn't go through a battery or a resistor is all of the same potential. So this all of that has the potential of 0 volts. Everything along that red line doesn't go through a resistor, only goes through wire, doesn't go through a battery, all has the same potential. And the other thing that we know is that over on this side, the potential at A is 10 volts, because you go up across a 10 volt battery. You start at the negative end, which is attached to ground, so the negative end has a potential of 0, and then you go up 10 volts because you're going from negative to positive lead. So these currents, and you can just look at this, is that the current goes through here, splits, goes through those 2 resistors, recombines, and then goes back. It's the equivalent of if you had a water wheel The water wheel lifts the water up. The water goes down one waterfall. The stream forks, goes down two separate waterfalls, and then meets at the bottom. So we can think of visualize this as like water getting pumped up to the top of the hill. At the top of the hill, it comes down one waterfall, forks, and then at the bottom of the hill, they both dump into the same pool. So that's the visualization that I want to get across. What we have to do, the first task is finding REQ. That's the first thing we got to do. Now granted, we knocked out VA, VC, but that's trivial. When the work comes, we need to find REQ. REQ is the equivalent resistance. What we want to do is we want to simplify the circuit so that the three resistors can be replaced by one. What we want to do is we want to make something this complex look like this. And so we need to find that, because once we get REQ, then we can continue to other things. So what do we need to do to find REQ? We need to understand that resistors come in two ways. Resistors come in two ways, and in fact, capacitors come in the same two ways. They come in series. One of the reasons I don't like paper is that I can't just blank it out. Series and parallel. Though the one, he's still in class maybe? He's got an iPad Pro, which is awesome. It'd be exactly what I would use. But I don't have that $1,500. Series and parallel. With the series, the resistors come one after the other. With parallel, they go side by side. So series is bam, bam consecutively. The parallel is parallel. They go side by side. So right now what we see is definitely we have two resistors that are parallel. To find REQ, one must break down the circuit into more simpler parts that may be trivially combined. So when we have this circuit, So we have that. What we need to do is be able to draw a box around part of the circuit which only has one type of resistor assortment in it. In this particular case, within the red box, there are two resistors in parallel. They both start at the right point, they end at the right point or at the same point, so that we can combine them into that. R2-3 is the equivalent resistance of R2 and R3 together. What we have done, and this is the word that I use, it's not in the book, it is a creation of my own doing. I squooshed them. I squooshed 2 and 3 to become R2-3. Where there were once two resistors, squoosh, now there are only one. Now I look at this and I go, well, that's easy. I now have two resistors. No, that's not series, that's parallel. P-A-R-A-L-L-E-L, and that is series. So that is, R1 is in series with R2-3. That is an easy thing to do. So we squoosh them to be REQ. So when you're looking at a complex circuit, when you're looking at the back page of problem set 2, those circuits are far more complex than what we're doing right now. And so what you need to do is you need to look at those circuits and find the small parts within them that you go, oh, that's two resistors in parallel. I can yank that out, put in another resistor, and the circuit will never know. I pulled out R2 and 3, replaced it with R2-3, circuit never knew. Then I took R1 and that, replaced it with R equivalents, it never knew what happened. Thank you for asking. That is an awesome question. So really what I've been doing is I've been trying to do the physical science part. Now we're going to get into the math. So in the series, you don't, and bottom line question, what do you have to know about this for the sake of the test? You need to know how to apply the equations to do the problems. You need to know what I'm about to do here for the multiple choice and understand it. In a series circuit, this R1 and R2 can be replaced by R equivalent. And so what is, you pull out two resistors in series, you replace them with one resistor. How do we get this? The potential difference across R1 is delta V1. When any current passes through a resistor, there has to be a potential change or a potential difference. For R2, it is delta V2, and across R equivalent, it is delta VEQ. What relationship what is the existing relationship between delta V1, delta V2, and delta V equivalent? They add together to be equivalent. So you both said the right thing, put them together and it's perfect. If I drop down this waterfall and I drop down that waterfall, it has to be the same difference as dropping down that waterfall. So the delta V1 plus delta V2 is equal to delta V equivalent. There is also a current running through this, an I1, an I2, and an I equivalent. What is the relationship between I1, I2, and I equivalent? Who said that? Ah, you get points for snitching. All right. Let me ask you a question. You said I1 plus I2 is equal to I equivalent. Aren't these the same current? The current remains the same, so it doesn't fork. It stays the same. So let's say 10 gallons per second, we're going over the waterfall here, 10 gallons per second has to go through that waterfall. It doesn't disappear, so 10 gallons per second has to go through the whole thing. So it's not that they add, it's just that they equal. I1 is equal to I2, which is equal to I equivalent. Now, what we do to tie these things together is we use Ohm's law, and that I is equal to V over R, or V is equal to IR. We just rearranged it. Now, the way that I draw V and the way that I draw delta V, I kind of play a loose game with them. They're kind of the same thing, but I like to simplify it to this. So delta V1 becomes I1R1. Delta V2 becomes I2R2. And delta VEQ becomes IEQREQ. And as we've said before, the currents are all the same. So we divide all of these by itself. And we're left with R1 plus R2 is equal to REQ. And so those resistances are all the same, or those resistances add up. So to get the equivalent resistance of two resistors in series, you simply add them up. And if you had 30 resistors in series, all you would have to do is the same thing, R1 plus R2 plus R3 plus ... plus R30 equals REQ. The derivation holds for everything else. You can, as long as you have resistors in series, you can just add it up trivially. So the series resistors are pretty easy to set up. The parallel resistors now, to the person who said the currents add up and gave the wrong answer, be prepared to say the same words in a couple of minutes. We now have two resistors in parallel, R1, R2. They can be replaced by an REQ. They have current going through them, I1, I2, and IEQ. They have potential difference. I didn't draw enough space. And so we have the potential differences across each of these. Now, what is the relationship that we know between delta V1, delta V2, and delta V equivalent? They what? Okay. Incorrect. And you kind of said it. Had you said, all you got to do is add delta V1 and delta V2 to equal the equivalent potential difference, I would have respected you. It's still wrong. Why is it wrong? If you start at the top of a waterfall and you see two routes going down to the same pool, You and your buddy, you get into down one waterfall, your friend goes down the other waterfall. Who fell down the most? It's the same. So this is the equivalent of a waterfall it's forked. So both of them go down the same potential. So delta V1 plus delta V2. Oh, God, I'm listening to you. I'm sorry. Delta V1 is equal to delta V2. And that equals to the total potential of EQ. Had they ripped out both of those waterfalls and replaced them with one waterfall, you would still fall the same amount. So all those potential differences are the same. The other thing that we need to know, and now's the time for you, the two who have been getting it wrong, now's your time to shine. What do I know about the relationship between I1, I2, and I equivalent? They add up, exactly. And why is that? Because they fork. If you have 10 gallons per second coming out here, and you have to have 10 gallons per second coming out there. So if I1 was 4 gallons per second, I2 has to be 6. They add up correct. And so we get this. Once again, we take the equation that has the sum in it, because those two equations have parts of the equation which are of 1, 2, and equivalent. And we find that I1 is delta V1 over R1 plus delta V2 over R2 equals delta V equivalent over R equivalent. We know that all the potential differences are the same, and I'm left with 1 over R1 plus 1 over R2 is equal to 1 over R equivalent. Or you could say that R equivalent is 1 over R1 plus 1 over R2 inverted. So that is the equivalent of a parallel circuit. So let's go back to that. 25, 10, and 50. What you do with these circuits, I don't even care about the battery at the moment. The first thing that you do is you use this equation and that equation to apply them to these circuits, and you look for the simplest way. The simple thing that we did here is that I have one box of 2 resistors in parallel by itself. You can't, I'm not even going to draw it, I'll trace it. You can't combine those two because it's not a series circuit purely. It's a series combined with a parallel. So you have to do parts of this where it's only parallel or only series. You can't mix them together. So the first part, R2, 3, is 1 over R2 plus 1 over R3, and you invert it. That's the first step. You can start anywhere in the circuit as long as the circuit allows you to combine only series or only parallel. Oh, and the other thing about the parallel, if you had 30 resistors in parallel, you could do the derivation and it would end up being 1 over R1 plus 1 over R2 plus dot 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 plus 1 over R30. inverted is equal to R equivalent. So if they're all series or all parallel, you can just use these to simplify. This becomes 1 over 25 plus 1 over 10 inverted. When you work with these problems, this is one of the reasons, the other calculators may be able to do this, but I like this. If I did 25 plus 10 inverted and invert that, I get, I don't know if I can, there we go. So when I invert it, I get the 7.142857 blah, blah, blah. And a lot of you would just simplify it to either 7.1 or 7.14. To minimize, I call it bit rot, that slow growing inaccuracy of the numbers, use fractions when working the problems. Give final answers in decimal. And when we continue to look at this, it'll become plainly evident. So what I do is I hit this math button and then I go, it's already highlighted to convert to fraction, and I hit enter, enter, and it gives me a clean fraction of 50/7. And I want to keep that number. In the next part, I have a 50 ohm resistor with a 57th ohm resistor. So Req is equal to R1 plus R23, which is equal to 50 plus 50/7. And so that will give me 400/7. Or you could say, as a final answer, Req is equal to 57.14 ohms. So we found the first part. The first step to doing any of this is to find Req, the equivalent resistance. I could replace this entire circuit with one resistor, much like I did much like I did to this. And then now I've got one resistor with one battery. I can now do part 2, which is find I0. Now I0 is the current going through the battery. The current going through the battery is the potential difference of the battery divided by the R equivalence. That means I've got 400/7 divided by, whoops, not you, 10 divided by 400/7. And this is one of the reasons why I like to keep the fractions stored away in the computer, is that a lot of times what I'll try to do with the problem is set it up so that your final answer looks legitimate. This answer is 0.175 amp exact. Had you rounded and used 57.14, you would have not gotten that exact answer. Oop. Now in our circuit, I know what R equivalent is. I know what this battery is. I know what I naught is. So we'll still use our green for known quantities. I know what REQ is. That helped us get I naught. The easiest thing to do now is, it's the equivalent of a Sudoku puzzle. You look for the obvious parts first. You don't try to look at the area where you have no information. You look at the area where you can find you have all of the information already. What is the current of I1? 0.175. The current flowing through this battery, all of it has to go through there. So I1 is equal to 0.175 amps. Now things get a little bit more difficult, a little less trivial. I know that I2 plus I3 is equal to I1. That the current coming through the R1 resistor has to fork into I2 and I3. Part of it goes through the R2 resistor, part of it goes through the R3 resistor. There's a lot of stuff I don't know. I mean, I just thought of this. I call it, and I talked about this on Friday. Look at this one equation. Across every resistor, there is a current. At each end of the resistor, there is a high part and there is a low part, and there is a current connecting the two and a resistor that does the connecting. Look for places in the circuit where you know 3 of the 4 variables. So in this equation here, if I knew V high, V low, and R, I can get I. If I knew V high and V low and current, I could get resistance. Rearranging this, IR equals V high and V low. So V low is equal to V high minus IR, and V high is equal to V low plus IR. So those 4 starred equations are all equivalent. They're the same equation, just rearranged. It's once again another demonstration of the advantages of alphabet soup mode. So I've got to look at a part where I know I1, VA, and R1, R2, and R3, but I don't know I2, I3, or VB. So across R2, I don't know its current, I don't know VB, so that resistor I can't play with just yet. For R3, I don't know VB, and again, I don't know its current, so I can't play with this. But across R1, I know VA, I know R1, and I know I1. I can get VB. So with VB, it's the low potential. So it equals to VA minus I1 R1. The VA is 10. The I is 0.175. R1 is, what did I say? R1 is 50? Yeah. And so that gives me a value.
Did you say VB was your VI?
Oh, I'm sorry, I got those reversed. I'm sorry, hold on. I am correct. Please state the question so I can pummel you.
Are you saying VB is like VI or?
No, I did. Now look at the equation that I wrote here. VB equals VA minus I1 R1. What I did is I took this equation and substituted in. Exactly. I make so many mistakes I doubt myself, but occasionally I get it right and then I have to make an example of the student. So this becomes .25 exact. Remember, had you plugged and chugged, you would not be getting exact numbers. Now VB becomes a known quantity, and if I know VB, now for R2 and R3, I can go, I know my high, my low, I know the resistors each. I can find I2 and I can find I3. They become known quantities. So I2 is equal to VB minus VC over R2, which is 1.25 minus 0 over R2, which is 25. And that should give you, for a second I was going to say 5, but I know that's not right. 0.05. And then I3, which is VB minus VC over R3, which is 1.25 minus 0 over, what is R3? 10. So that gives me 0.125 amps. And one of the things that we look at, yeah, I'm good. All right. Now, to the people who gave the wrong answer or the right answer at the wrong time, which made it a wrong answer, what do you know about the currents going through a parallel set of parallel resistors? They add up to be, yeah. So I2 plus I3 is equal to 0.05 plus 0.125, which is 0.175 amps, which is equal to I0. Exact. Once again, what I'm stressing, it's one of the whole reasons why I've been stressing about using the fractions, is if you don't use the fractions in your calculations, it is 100% certain that you will not get you could not add up I2 and I3 to get your final answer. There would be uncertainties. With using fractions, you get exact answers. And if you get exact answers that add up and look right, then you can go in with confidence and turn in the problem and get your full credit. If they don't add up, then you got issues, and then you got to go back. By rounding numbers, you're introducing uncertainty, and that's something that it lowers your confidence. Now, this is something that can work trying to think of the English way to say this. What we're going to do is we're going to verify V sub B from the bottom. And what I'm going to do is I'm going to rewrite my circuit as R1 and R2, 3. So this is, in fact, I don't really care about what's going on over here. All I want to know is VB and VC. R2, 3 is an equivalent resistor. R2, 3 is effectively R2 and R3 pulled out with a single resistor replaced. The goal is to just find VB. All I want is VB. I don't care about the currents going through each of the resistors. The one thing that I know about R2, 3 is that current I0 is flowing through it. Equivalent resistances may be used in this equation. It eliminates, can't spell eliminate, it eliminates having to know the specifics, in this case, the specifics of I2 and I3. I don't have to know I2 and I3. If I can get R2, 3, I know I0 goes through it. So I can just simplify it to this. And get VB. So in this particular case, VB is the high, VC is the low. So V high is IR plus V low. This I is I0. The R is R2, 3. The V low is the ground, which is 0. So I don't really care about that. So this becomes 0.175 R2, 3. Goodness, go back in the notes. Is 50/7 and I'm left with 1.25 volts, which checks from the other direction. So one of the things that I do when I'm working with a complex circuit is when I do all my squooshing, one of the things that I keep track of is all of the intermediate resistances and their specific values and fractions. Because it may become important at a later time that I may have to use them in situations where I don't know anything about the current going on within it, but I know the total current, so I just can use the equivalent resistance for that subset. And so I can bypass a lot of garbage in order to focus on the big picture. Now, the way that I'm gonna have to move on to capacitors right now, but what I plan on doing is a lot of the circuits that are, those are due on Friday. So we've still got Thursday and Friday to get into way more complex stuff. This is just the basics so that you can kind of work with the lab this afternoon. And then the harder stuff we'll get to later. With Russian Review, it's kind of a hit the highlights and then we'll fill in everything else a little bit later on. But those, what have I been trying to do? I've been trying to teach you how to fish rather than catch a specific fish. So what I've been trying to do is teach you the generality, the general solution to doing all of this. If you take those rules and apply it to the other stuff, it's just more complex. It's a little bit more tedious, but it's the same thing. All right. Capacitors, they behave like odd batteries. They charge and discharge. And similarly to the talk about resistors, what I'm going to do is I'm going to talk about capacitors in kind of a general term, and then we're going to do some basic like a kind of a problem with it, and then we'll keep working on it. A charging a charging capacitor, you have the battery, you have the capacitor, you have the resistor, and then you got a switch. So these three are all in series with each other. There is the discharging arrangement where you have, now technically for a capacitor when you draw it, you don't draw a line in between. So when it's discharging, the battery is out of the circuit. There's been a disconnect. And so you get this. The current, really we're not particularly interested in not as interested in as with the resistors. We're kind of in the overview of the things that we'll be looking for across this capacitor is the charge on capacitor, which is Q. We'll need to know the delta V across C, which we'll just use as delta V. And the time it takes to do this. And we could also say the current in the circuit, which we will say as I. So those are the four big things for these capacitors. Now we've talked briefly about capacitors in the analogy of you've got the two sides of the room, you've got a gap in the middle, you've got two plates, each of area A. The restrictions are the area for each plate well, the 214 capacitors. You can get weird with the 212 capacitors. But in our particular game, the area for each of the plates is identical in area and, well, for each plate is identical in size and geometry. Actually, I should probably write it more as area. So if one is 10 square centimeters, the other one has to be 10 square centimeters. If the other one is square, the other plate is square. If one is circular, the other one is circle. If one is oval, the other one is oval. We're not really going to play games with this, except for that C is equal to epsilon naught A over D. And we've discussed this before. The epsilon naught is a constant. It's the permittivity of free space. A is the area, and D is the distance between the plates. So we have this. And there are some basic equations, or there may be a problem or two. I'm going to check the capacitor problems. And there are no problems in any of this, so we're not really going to go through this in depth. But what we do, I got to talk about this. When you have a let's say for the moment you have a capacitor, and that capacitor is uncharged, and I'm not really worried about the resistor in this case. The battery has its positive end and its negative end. And initially within the wire, you have all of these negative particles evenly distributed throughout the wire. If you've got a hunk of wire, you've got a distribution of free electrons just hanging out, minding its own business. and you flip the switch and you now start letting this circuit do whatever it needs to do. And what happens is the battery starts pumping electrons from higher potential to lower potential. And so kind of in an intermediate, let's just keep these numbers, 1, 2, 3, 4, 5, 6, 7. There will be, so 3 come over, 6, 7, 8, 9. 1, 2, 3. Electrons will start flowing from one side of the battery to the other. It starts pumping electrons, much like say this room was just sealed and there was a fan in the wall and it was just trying to pump air out of the room into the atmosphere. Initially it would be kind of successful in doing it because the pressure between us and the outside is kind of equal. So it starts doing this. But eventually there is a great imbalance in these electrons within the circuit. Eventually, the difference in pressure between the inside and the outside of the room becomes so great that the power of the fan, it just can't suck any more air out of the room. Eventually, this imbalance becomes so great that this battery, let's say the battery was like V naught. Sometimes I go battery strengths as V naught. The potential difference across this capacitor initially is 0. Now, the potential difference across this battery is greater than 0, but less than V naught. And eventually, that delta V is equal to V naught. So in charging, it starts here. There's an even distribution of electrons. The battery kicks on. The electrons go from positive to negative side and then just start getting kicked out. And eventually, this great imbalance is enough that the capacitor becomes charged and it becomes fully charged. What ends up happening is that that plate over here has a deficit. And remember, what is a positive charge when we're thinking about electronics? A deficit of electrons. This has an excess of electrons, so that plate becomes the negative side. And eventually, the potential difference of the battery is equal to, or the potential difference of the capacitor is equal to the potential difference of the battery. And then the whole thing starts off. Small imbalance, significant current, significant but decreasing current, no current, and fully charged. The relationship that we need to understand for something like this is that the charge on these plates, their magnitudes is CV, the capacitance of the capacitor and the potential difference of the battery. So in this case, it would be V naught. That would be the capacitor, which we would get from this or get it from some other way. This is the magnitude of the charge on each plate. And one of the things that we kind of need to talk about in terms of all this stuff is, you know how passionate I am about units, and we haven't really talked about it. Maybe on Friday we did, but that was like 5 days ago. Who knows what happened then. Capacitance is measured in farads, which is F. And just as a reference, typical capacitances are in millitesla, or I'm sorry, not, why am I doing that? Millifarads. If you had a 1 farad capacitor, that's a big capacitor. That thing can absorb a lot. The typical capacitors that we'll be dealing with in the lab are on the order of tens of millifarads, stuff like that. All right. Capacitors have their equivalences. You could have series and you could have parallel capacitors. The series capacitors look like this. The parallel capacitors look like that. And so you can squeeze them down or squish them down into their equivalent capacitances. And you will be given, problem set 3 is a perfect example of equivalent capacitances in just big circuits. Now, we're not interested in the individual currents passing through this whole thing. In terms of expectations for what we want in 214, we're not really going to be interested in it. What we are interested in is understanding how to get the equivalent capacitances, because the ideas behind them, A, are important and B will be in the multiple choice. We're only thinking about this. These are fully charged capacitors. We're not really interested in their in-between states just yet. These are fully charged. So delta VEQ is across there. Delta VEQ is across there. Delta V1 and delta V2. Delta V1 and delta V2 is there. And we look at the similarities between this and their resistor equivalent circuits. And when you've got these two delta V's side by side, you know that the delta VEQ is equal to delta V1 plus delta V2. And over here, you know that delta V1 is equal to delta V2, which is equal to delta VEQ. So those potential differences must be the same if they're in parallel. Just like two resistors in parallel, those resistances must have equal potential differences. The thing that we have to talk about now is the charge. The charge on a if you had a charged and an uncharged capacitor, one where there is Q and negative Q, and this has no difference, what this charge sees is a whole bunch of uncharged area. The charge will redistribute until that's a prime. It'll redistribute, so it's Q prime, negative Q prime, Q prime, negative Q prime. So the plates will again reorganize, and this is all about potential differences within the capacitor, free electrons floating around. The charges will redistribute. So the identity that we have to use for something like this is that Q1 is equal to Q2, which is equal to Q3, or Q equivalent. This is when they're fully charged. So if you've got a charge of 1 coulomb on the plates of C1, there's got to be 1 coulomb of charge each on the plates of C2. And if you replace it with equivalent capacitance or equivalent capacitor, it's got to be the same thing. With parallel capacitors, it's a lot like so in this particular case, what I've done is 2 circular plates, and I've kind of drawn a line in half, and so you can kind of split them. Parallel capacitors, it's a lot like what you do is the distance, well, it can't be the distances. So the equivalent capacitance is a lot like capacitors where the areas are merged together, where the charges are merged together, where the charges add together. And Q1 plus Q2 is equal to Q equivalent. So the charges on series capacitors have to be equal. The charges on parallel capacitors are allowed to add up. And you get this. Now let's use, what was the technique that we used before for resistors? We look at the one where you've got to add stuff up. So we have, for series, you can leave that door open now because they've moved on, hopefully. Delta VEQ is equal to delta V1 plus delta V2. In parallel, delta V1 equals delta V2 equals delta V equivalent. No, not that one. Q1 plus Q2 is equal to Q equivalent. So those are the 2 equations for each of these that you set up. And then what we do is we use variance of Q equals CV. So this becomes C1 V1 plus C2 V2 is equal to C equivalent, V equivalent. The potentials are the same, so C1 plus C2 is equal to C equivalent. So those potential or those capacitances for parallel add up. And what you know is a parallel capacitor, their capacitances add up like resistances of series resistors, that the math looks the same. For series capacitors, we use Q over C is equal to V. So VEQ becomes Q1 over C1, Q2 over C2, Q3, or equivalent 1 over C1. So that goes that and that goes that. But what do we know about the charges in a series capacitor? That they're equal to each other, so they cancel. And we're left with CEQ inverted is equal to 1 over C2. Hold on. 1 over, stop skipping steps, Vance. And so the series capacitances look like parallel resistors, 1 over REQ, 1 over R1 plus 1 over R2. And so I'm just showing you the similarities in the equations. And the procedure that you do in problem set 3 is the same as finding the equivalent resistances that we did all the way back here. So if these were capacitors, you would just take R2 and add it to R3 to get R23, because then you could draw a box around the two. And then if you have two series capacitors, you add them up using this equation. And what we'll do is on tomorrow and Friday, we're not done yet. I still got 20 minutes I'm going to use, or 15. We're going to add up the more complex stuff and get a little bit more detailed. But the last bit of things that I need to cover for test 1 material is charging RC circuits and discharging RC circuits. So in the series or in the charging and discharging circuits, it's the equivalent of all of this. We've got a battery, the capacitor is discharged, we let the current flow. When it comes to a stop, what's the charge on the capacitor? All that fun stuff. Then we switch and we start discharging. The energy in the capacitor starts going through the resistor until eventually it's discharged. The thing that we look for is the V, the potential difference across this capacitor for a charging is 1 minus e to the negative t over tau times V naught. V naught is the battery. T is time, and tau is the time constant. And we'll get to that in a moment. So T is time, the squiggly T is a tau, the V naught is the battery, and then there's this 1 minus e to the negative blah blah in the middle. For a discharging circuit, the potential difference across the capacitor is V max e to the negative t over tau. T is the time, tau is the time constant. This V max is the max for capacitor, which is in 214 almost always the battery. What we usually say in these problems is you hook this RC circuit up to a battery of 100 volts, you let it fully charge, then you disconnect the battery and let it discharge. Well, the maximum voltage is the maximum voltage of the battery. So it's effectively V naught or whatever battery strength you got. And you have these. Tau, time constant. Now with tau is simply the product of the resistance and the capacitance of the circuit. So when you got a resistor and a capacitor in series, those things are and in number 5 I ask you to do it. You multiply them together. Resistance is measured in ohms, capacitors is measured in farads, tau is measured in seconds. And problem number 5, and we may end up doing this either Thursday or Friday, problem number 5 on problem set 3 is, show me how ohms times farads gives me seconds. How does a second pop out of those two complex things? And it's just some unit play. Just play with units and a few equations. This tau and the equations make these plot lines look like that. So rather than linear lines, these things are exponential curves. And we'll go more into detail. Really what I'm doing is I'm trying to do some basic stuff, and we'll fill in the gaps tomorrow and Friday. This is for a charging. This is for discharging. Now obviously the horizontal is time. The vertical is the potential across the capacitors. Charging means this potential difference increases. Discharging means the potential is decreasing. One of the things that tends to be confusing to a lot of students is I'm going to write these equations down on your equation sheet on the test. But a lot of times people get confused with why is this discharging and why is that, why is this charging and why is that discharging? And to understand the differences between the equations, look at look how it behaves when time is 0 and time is infinity. And just plug in those numbers and see what happens. So in the case of time equaling 0, e to the negative 0 over tau becomes e to the negative 0. Now what is e to the 0 or negative 0? It's 1. So this part becomes 1. And 1 minus 1 becomes 0. So initially, at time equals 0, V is 0. That's definitely a charging, that's what you would expect to have a charging capacitor at time equals 0, a potential difference of 0. If time is infinity, e to the negative infinity over tau becomes 1 over e to the infinity over tau, which becomes 0. So if t is infinity, e to the negative infinity makes it 0. 1 minus 0 is 1. So this just becomes V naught. So at t is infinity, V naught becomes, V becomes V naught. For this, if t equals 0, e to the negative 0 over tau becomes 1, so V equals V max. At t equals infinity, e to the negative infinity over tau becomes 1 over e to the infinity over tau, which becomes 0. And V is equal to 0. And so that's how you can figure it out. You look at the equations and go, I don't know if this is charging or discharging. Well, if you plug in t equals 0, V is V max. That's a discharging equation. If t equals 0 here, this gives me V equals 0. That's a charging equation. So you just plug in the endpoints and then you can see what happens. The last thing that I'm going to do is do a simple an RC circuit is charged with a 100-volt battery. If tau is equal to 20 seconds, when will V equals the potential difference across the capacitor, when will it equal 70 volts? So you have a basic RC circuit, you're charging it up, the battery gives it a 100-volt potential difference, the battery starts charging. When is the potential difference across this capacitor 100 volts? So you're charging. V equals 1 minus e to the negative t over tau, V naught, or V of the battery, or electromotive force of the battery, or whatever you want to call it. When is that potential 70 volts? So I have to find out T. I know tau, I know V naught, that's the battery, or 100. Find T. So this is how we solve it mathematically. V over V naught is equal to 1 minus e to the negative t over tau. Then I'm going to put this over here and that over there. E to the negative t over tau is equal to 1 minus v over v naught. And I get this. Now, how do we deal with these exponentials? Well, in mathematics, one of the things that we can do is similarly, if you have x squared and you wrap it in a square root, they cancel out and you're left with x. What we do is, with something like this, if you've got e to the a and you wrap that e to the a with a natural log, you get a. That's how you get rid of the exponential to solve for t. So you wrap these and you should do it to both sides, just a tip. And you get this. The natural log and the exponential cancel. And you get this. So now time is negative tau natural log 1 minus v over v naught. And you get this. Now, a lot of people would be bothered by the fact that there's a negative symbol out front when you're dealing with time. Time tends to be a positive quantity. Well, one of the things about natural logs is this is going to give you 1 minus this is going to give you a fraction of 1. And the natural log of anything less than 1 is going to give you a negative number. So t is negative 20 natural log 1 minus 70 over 100. And that will give you 24.1 seconds. And so that's the general math that you have to use for something like this. And what we're going to do on Thursday and Friday is that we're going to start filling in a lot of the gaps. What we covered in the first hour should be good enough to handle Ohm's law. And then when we work, you guys are doing series in parallel on Thursday. We'll definitely be ready by then for that. All right, that's it.